Okay, so this is Lab 8, where um, we are testing landing gear by dropping it from three different heights and basically getting readings on the acceleration and the amount that the actuator arm um, hooked up to the wheel, how much it changes, and yeah, we are group 11. So our objectives are to implement the use of a photodiode by shooting a laser um, into a mirror, and then when we drop the landing gear and the landing gear interferes with the laser, that's when a trigger is set off, and that's when the data will be recorded. Um, and that and then we will find and plot the acceleration and stroke length of the landing gear system um, for different vertical drop heights. Next slide. So the tools that we use for this lab, we have a small mock landing gear system that's attached to um, a sliding thing so that it drops straight vertically. We have a piezoelectric accelerometer hooked onto the landing gear system, and then we have a rotary potentiometer, which is hooked onto the joint that connects the um, actuator to the rest of the landing gear. And then those electrical signals are all hooked into the LabVIEW DAC system so that we can turn these signals into graphs. So here's the setup of our LabVIEW um, screen. So we have three sets of data coming in. We have the acceleration, we have the rotary sensor, and we have the photodiode sensor. And all three of these are measuring different things. And so we have three different waveform graphs for that. And then we also have this trigger system, which tells us when it tells LabVIEW when to start recording and when to stop recording based on when that trigger is met. Next slide. So here's a picture of the trigger function settings. Um, we basically shot a laser at the mirror and we got a value um, for that reading, and then we got a value of the voltage when the laser was not on, and basically the mean value between those two is um, the trigger point that we used, and that's basically the most important thing here. Yeah.
All right, this is the apparatus. Um, on the left, we have the diagram. You can see the landing gear setup. It's got the spring and damper system. And then we have our three sensors. The piezoelectric accelerometer is on top there, rotary potentiometer, is at that pivot joint, and then the photodiode lined up with the laser pointer. On the right, we have the actual picture of the setup. As you can see, all the parts are still there. Photodiode and the rotary potentiometer, a little blocked, but they're back behind there for when, and then when the system is lifted up, the photodiode receives the laser. And then this is just the photodiode circuit. Takes the light coming in and through the circuit, has an incoming voltage, and then produces the output voltage, which we then read through the DAC system. The first part of the procedure, photodiode calibration. Again, we focused the laser pointer at the unblocked photodiode and then recorded the voltage output with both the laser on and off. And then just finding a middle value between there allowed us to have a trigger value for when we set up the automated drop. So we could just plug that into the trigger function for that part. And then the procedure for the drop part of the lab, where we're actually dropping the landing gear. First connected the accelerometer and rotary potentiometer, as I just showed in the apparatus. Again, the VI we previously showed, built that on LabVIEW to record voltage outputs from the accelerometer and potentiometer. It also does record the voltage output from the photodiode, but that's more of just used as a trigger to start the recording. So when that trigger value is crossed, the automated system goes ahead and starts the value recordings of both acceleration and angle. And then for the actual experiment, we raised the landing gear to a height and then dropped it, allowing free fall, crossing the photodiode, breaking it, and allowing the collection of acceleration and angle data. And then we did this for 3 different heights. For our lab, we did 175 millimeters, 275, and 375.
And now for this next part, we have the photodiode trigger value. So there was an unblocked value of 2.7 and a blocked value of 0. And in order to trigger the photodiode, rough values were acceptable, since just a middle value between a range was required for the trigger. So we set this to a value of 1.5. And yeah, that allowed us to collect data once it was triggered. So now we have some calculations, and this is for the transient acceleration. So from the piezoelectric accelerometer, the transient acceleration can be calculated using the following equation. So in this equation, C piezo is the piezoelectric accelerometer constant, G is gravity, and V is the voltage adjusted for initial conditions before excitation. So now for this next one, we have the rotary potentiometer calibration chart. So this chart shows an output voltage percentage versus the angle. And this chart shows a linear relationship between the voltage ratio and the output angle. And for the angle, we just multiply the ratio by the nominal angle using the modified voltage divided by, in this case, Vs, which is the angle sensor's 5 voltage bias voltage. So next for our calculations, we have the angle of the landing gear. So from the angle sensor, the angle of the landing gear is shown below in this equation. And similar to what we previously talked about, the V is representing voltage. And now we have stroke length calculations. So this has a relationship of H naught over A. And to find the stroke length, we subtract the H value as shown on the diagram on the right from the H naught value. Yeah.
For clarification, the TA dataset is used instead of our groups collected dataset because our rotary potentiometer readings were bad. In our lab setup, the piston arm was not actually working, it was stiff. So the readings did not detect a big change or actually any change at all in the angle. Therefore, we decided to duplicate the TA dataset. Next slide. Here we have the photodiode voltage over time. We see that at 3 seconds, or there is 3 seconds of high voltage, and then a sudden drop to a low voltage for the last 5 seconds or so. This shows that the photodiode does work properly because the voltage recorded drops sharply at 3 seconds, which is roughly when the landing gear is blocking the laser to the photodiode. Therefore, we can move on to analyzing the voltage readings from the rotor potentiometer and the piezo accelerometer. Next slide. Here we have the voltage over time for the rotary potentiometer. The voltage readings from the potentiometer starts low, and then a peak occurs around 3 seconds, and finally drops to a different higher voltage. This phenomenon makes sense since the voltage corresponds to the angular displacement of the landing gear. The starting voltage should be different when held in the air, and then the peak is explained by some spring motion of the piston arm as it hits the table. And then finally, the landing gear lands and sits at the table at a static angle, a certain angle. Next slide. Here we have the voltage over time for the piezo electric accelerometer. The piezo voltage readings is the same as before, before and after the landing occurs, which makes sense because the acceleration should be about 0 meters per second squared before and after the drop because it's not moving at all. At 3 seconds, though, we do see first the big initial uptick, which that indicates the landing gear falling, and then the big negative acceleration, which indicates the landing gear hitting the table and then springing backwards. Next slide. Here we have the acceleration graphs. Again, the acceleration before and after we see is 0 meters per second squared. We see an increase up to 100 meter per second squared, which is falling and experiencing acceleration due to gravity. That's why it's about 10 or 9.8 to be exact. And then it experiences a big negative acceleration as it hits the table and it springs back up. And then it's stops moving and experiences 0 meters per second squared of acceleration. Next slide. Here we have the angle graphs. The initial angle is higher than the final angle, and there is a big drop at 3 seconds of impact, or the 3 seconds, which is the impact. This makes sense because we expect the initial angle to be larger than the final angle, where the final angle is the landing gear sitting on the table, and the initial is the lab experimenter holding it up. However, do take note that the final angles in all 3 of these high drops are slightly different. This is likely an error from the potentiometers, like data collection itself, as the angles, physically, they should be the same when it lands and when it is at static equilibrium, regardless of wherever it starts. Next slide. Finally, we have the stroke length graphs. We have here in the graphs, we set the initial stroke length to be 0 inches. And then the landing gear experience a sudden change in stroke value at roughly a difference at roughly a tenth of a fraction of inch or inch, which makes sense. It's pretty reasonable. Once again, the final stroke lengths vary again for all three of the heights, even though they should be the same physically, the same value when the landing gear is at static equilibrium. Next slide.
All right. In conclusion, we did complete all the lab objectives successfully. Again, we did end up using TA data due to sensor failure for our data. But objectives, adding a trigger compared to previous labs where we had to manually start and stop data collection, we added a trigger allowing for automatic data collection, and results for both acceleration and stroke length. Acceleration, the peaks increase with drop height as expected due to being there's more velocity that decreases on impact, leading to higher acceleration. And then stroke length also increased as there's more, the spring compressed further on the landing gear with increasing height. Thank you.